All right, so in our second set of learning targets here in Chapter 3, in 3.7, we are going to look at different types of graphs. Now, gone are the days where I feel like we need to practice creating these graphs. We are in the 21st century, and any expectation moving forward, if you are creating any sort of data summary, whether it be for college or for your place of employment, I would assume it would be expected that we do that on computer. And so what this section of notes will be for is just, not necessarily learning, because I think you've seen all these before, but just reviewing and going over the differences and interpreting, when does it make sense to use a bar graph versus a pie chart versus a stem and leaf plot versus a histogram, etc. And so again, I might skip a couple things here because we will not be creating any of these by hand, but instead later we will be learning how to do that on Google Sheets. So when you are displaying data, again, that's kind of the topic for today, displaying different types of data. Here's a data chart table, which technically is a form of representing data, is just in a table, of the different levels of education, the number of people, so the count in each category, and then the percentage. Sometimes the rates, the percentage of a statistic, can be more helpful to understanding data. For example, in these numbers are in thousands, so after every number add 3 zeros is what that means at the end of it. And so, for example, it is a lot, but having 5.1 million people not graduate high school is, don't get me wrong, that is a big number. We would definitely, obviously we want that number to be at 0, but then we consider, well, that's not even 13% of the population, and that number maybe doesn't seem quite as bad. Again, in a perfect world, that number is at 0, and so I get that is bad no matter what. But again, when we look at it as a percentage, then we understand more that that's actually not too bad. Okay, and so a lot of times percentages can be helpful in that way. Now, on the other side, it can be misleading. Okay, for example, let's say you survey 10 people out of, again, let's use Mount Westonka High School, 1,000 people in the high school, and you survey 10. And from those 10 people, 5 of them say that they love gym class, Phi Ed. It would not be fair to say 50% of Mount Westonka High School likes Phi Ed. That would be very misleading since we only interviewed 10 people and the count is 5. So especially when we're talking about bigger data sets, rates, percentages can be more helpful, but that doesn't say it's always the best way to go. The distribution, of a variable tells us what values the variable takes and how often it takes these values. So the distribution, both of these are called different types of distributions. Okay, the percent and then also just the straight count of the number of people that fall into a certain category are the distributions. So bar graph versus pie chart. The obvious is when we are talking in percentages, typically a pie chart is going to be better. When we are talking about a count, typically a bar graph is going to be better. Although you can tell that, or you can see on this example that it is possible to make a bar graph using percentages. Again, typically that's not often how we do it, but it is possible. And so, some pros and cons to each. Visually, it's easier to compare the height of bars than it is to compare the area of sectors. And, we take away the percentages from this pie chart, and let's just say we had, again, no percentages, just the different colors. It would be pretty hard to tell the difference between a high school grad and a bachelor's degree. Not impossible by any means, but it's hard to tell how different they are. And then same thing, especially with high school grad and some college. I mean, they're almost the same, so it's hard to tell that there'd be any difference. And so it's just harder to compare uh, visually. Now, numerically, again, comparing parts to a whole, in other words, a percentage is always a little bit easier. Okay. Bar graphs are easier to create. Again, we're kind of talking by hand in that sense because on Google Sheets you'll find that they're both equally as easy or equally as difficult. But bar graphs by hand are easier to draw. And again, bar graphs typically are used when you're comparing quantities. Pie charts are used when you're comparing parts to a whole. Both of them can be used, are used to display distributions for categorical variables. Remember, categorical variables are variables that are like gender, eye color. They're different characteristics. They're variables that you would not find have any sort of arithmetic meaning behind. So finding the average or the median or something like that. Okay. Another way to measure or to display data is a line graph. Typically, a line graph is measuring some sort of quantitative variable over a period of time for line graphs. And so that's those kind of the scenario that you're going to use line graphs for. Again, a quantitative variable like the price of a stock over some sort of period of time. So monthly, yearly, daily, even hourly. You can do it as well. And when we look at line graphs, we are looking for trends, which is a long-term upward or downward movement over a certain period of time. Okay? But we need to make sure that our scales are consistent. Here shows the same two sets of data, but notice that the data on the right looks a lot different than the data on the left. On the right, I see some, from 1978 to 1981, I see a pretty significant growth that we can't see in this chart. And notice that on this chart, the scale is not consistent. It counts up every 2 years, and oh no, it is consistent throughout that way. Oh, sorry, lost my train of thought. The scales are consistent. This is every 5 years, but because of the shorter time frame, you kind of can interpret different results. This is measuring the number of unmarried couples, and it looks like it has climbed significantly when we count by every 2 years, but then it's quite a bit different. It looks not quite as significant when we count every 5 years. So you need to make sure that they are consistent. And again, sorry, I lost my train of thought there. This is counting by fives, that's counting by twos, so that's good. But you need to then consider the scales that we are counting by there. Okay. Stem and leaf plots. We use stem and leaf plots to display quantitative variables with field values. So, if we did ask 1,000 people at Mount Wasanka a particular question, a quantitative variable, it wouldn't make sense to make a stem and leaf plot. That would take way too long. Okay. Again, these are supposed to quickly summarize data, and oftentimes stem and leaf plots don't do that. So honestly, a stem and leaf plot is something that we typically don't use. What it does help with is just organizing data. Okay. So just like going back and looking at this table, and this table the data has been organized. Stem and leaf plots organize data in a lot of the same way. Okay, so in this chart here, in a stem and leaf plot, it's called stem and leaf plots because the first column here is your stem column, and then everything else is on the other side is called a leaf. Okay, and this plot shows some sort of a percentage of data, and so to interpret this chart in particular, you will always have as many numbers as you want in the stem column. Okay, so you can see in our chart it could be one number, so in the single digits, or it could be double digits in this case. Okay, but the leaf must just be a single digit. Okay, so when you look, like if I look at the 12 column, since we just have it highlighted there, in this data, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different numbers that are in the 12% range. Okay, because we know that there has to only be one number in the leaf column representing. Okay, and specifically the number that's circled there, that would represent, in this case, 12.2%. Okay, but your stem column can have as many digits as you need, but the leaf column should always have one. Okay, so that we know, first of all, when you put it in order, then we can tell how many times a digit repeats. Like, again, in this data, whatever it might represent, 3 people got 13%. 3 more people got 13.1, only 1 person got 13.2, etc. Okay, so in that leaf column, every digit represents a piece of data. Okay, and so we have obviously quite a few pieces of data in this one set. Again, stem and leaf plot is hard to gain much knowledge from. It's much more of an organizational tool than it is to take anything away from. All right. That said, you can, again, take a little bit away. And we're going to use this terminology when we're talking about histograms as well here in a little bit. But when you are describing the overall pattern of a distribution, we talk about the center, the shape, and the spread. Okay, the center is quite literally the midpoint that splits the values. In other words, we know this to be called the median. Okay, it's the middle number in all of the values is called the center. Okay, the shape of the graph is the number of peaks. Okay, and again, this also will apply to histograms. And then the spread is the smallest and largest values, ignoring any outliers. And later in chapter 3, we will talk about how to find outliers. And so we'll be putting some multiple ideas together. But if I look at that last data set, again, you can almost view it as a graph where, if I draw this kind of imaginary line, I guess it's not a line, but this imaginary curve, okay, my data is shaped something like that. Okay, so the shape of the data is that it has one peak to it. All right, to find the center, to find the median, back when you first learned how to find medians, you kind of did the cross the first number out, cross the last number. And so that's how we do it here. And again, this is just another good example of why stem and leaf plots just aren't a great way to take anything super meaningful from, because this right here is a very tedious process, especially nowadays when we have, are we getting there? All right, boom. All right, looks like the center of this is 13.0%. Okay. And then the spread is basically your min and max. It's the smallest and largest values. And so the smallest value in this case is 7.0. The biggest value is 17.0. Okay, so again, some meaningful information here. It gives you the min and the max. It tells you kind of the shape of the graph. If there were multiple peaks, that would be something we could look into. And it gives you the center, but again, just not super convenient to find it that way. Histograms. Histograms are like bar charts, okay? But histograms are only for quantitative variables, okay? Not categorical, just quantitative variables. And specifically when the quantitative variables are nearby each other, okay? And so says when quantitative variables have lots of values, and the distribution occurs if nearby values are grouped equally. Okay, when they are grouped equally. All right, so below we have a graph of tuition and fees charged by 90 Michigan colleges. So imagine making a bar graph with 90 different bars. Probably not very realistic, right? That's going to be a lot of work. So instead, we make a histogram. Okay, a histogram is like a bar chart, but the bars are touching. All right, and so the way to read these bars, let's look at the scale. It looks like they're counting by 3,000s, but they've only labeled every 6,000. But so in other words, when I read this bar here, this first one, I would read that as that there are 24 schools that charge from 0 to 3,000 in tuition. Colleges 2008, I'm guessing per year. Okay, that's what that bar means. Again, it represents a range of values. All right, and then the next bar is 3,000 to 6,000. So there were 7 schools that did that. And then the next bar, 6 to 9 was 19, 9 to 12 was 9, and so on. And that follows that pattern. Okay. And so that's, again, the difference between bar graphs and histograms. When you're making a histogram, make sure that these chunks are the same. So every chunk represents 3,000. They should always be distributed evenly to be a fair representation. And we can answer the same questions that we did before. Okay. Again, this graph looks a little bit different. If I were to draw it with the curve, there we go. Now, you don't need to follow the graph exactly. So you just draw kind of this rough curve here that looks something like that, almost like an exponential function. And so the shape of this graph is it still has one peak, okay? Because I know there is that 7 bar right here, but in general, that the shape of this graph is that it just kind of declines as the tuition gets higher. The center of that going to be a little bit trickier, but let's see what we can do here. So we have, let's figure out how many total schools. Oh, they told us 90 total schools. So the center would be the 45th school. Okay, so let's find where the center of that is. So we have 24 plus 7 is 31, and then plus 19 is 50. And so the center in this case would be between, because this is a histogram, we would say it as a range. The center would be between $6,000 and $9,000. Okay. Again, there are 90 schools, so the middle data point would be the 45th school. And although we don't know exactly where, the 45th school falls somewhere in this bar, and so that's the $6,000 to $9,000 bar. Okay. And then the spread. Now, again, this doesn't do a great job of giving us exact numbers, okay? But so in this case, we know that the spread, all we know about the spread is that it's somewhere from $0 to the end of the graph goes to 33,000, okay? Again, pros and cons of all distribution sets. And in this case, a stem and leaf plot was actually a lot better to see the min and max, to see the spread. And in this case, a histogram is not that great. I mean, it gives us a rough idea of what it looks like, but just in the exact values, we don't know what the exact min or what exact max are. Okay. Again, we're not going to, it's gone are the days where we need to worry about trying to make a histogram by hand. So go ahead and skip that. And last thing we'll look at here is symmetric or skewed distributions. So a symmetric distribution is where the left and right sides are mirror images. So when you draw your little curve, symmetric is where the curve is right in the center. Okay. A distribution is skewed to the right if the right side of the graph extends much further than the left. So this is probably backwards to what you think. But a distribution is skewed to the right if the right side has what we call a tail. Okay? So if this is the center of the data, a lot of the data falls on the left side, but we actually say it's skewed to the right because that's where the tail is. And vice versa. Now, if this is the center, here's my tail. And so this is skewed left. Oops, this is skewed left because that's where the tail is. And so if I look back at the data point or at the data sets that we had where we drew that curve, okay, oops, that must have been on the, there it is. Okay, in terms of the skew, all right, this one was more symmetric, okay, because again, it's not perfect, but it is close to being right in the middle. So I would say it's more symmetric than it is skewed to, if we were to rotate it, it'd be skewed left. On the other hand, our histogram is definitely skewed right. All right, that tail on the right side is definitely nowhere near the middle, and so this would be an example of a data set that is skewed right. Okay, but again, data can be interpreted in different ways, and so you heard what I had said here is if you could definitely make an argument that this is skewed left because it's not perfectly in the center. The way that I interpret it is that it's close enough to symmetrical that I would consider it more symmetrical than skewed left. Okay, but again, data can be interpreted in different ways. And so that's 3.7. Okay, again, not creating these different charts, but learning how to read them and learning when to use which one. When does it make sense to use a histogram versus a bar graph versus a pie chart? Okay, versus a line graph. All right.